Math 1332, Chapter 3, Symbolic Logic, Section 3, Types of Statements, Video 1, Tautologies and Self-Contradictions. In this chapter, we're going to use our truth table building skills to identify types of statements. And so here we go. All right, so let's consider this statement. If I go to college and I take math, then I go to college. That statement sounds kind of redundant. It seems like this statement should automatically be true, especially if you ignore the second half of the conjunction. Notice that this statement is a conditional, if then, but in the consequent, we have a conjunction. And if we ignore the second half of that conjunction, then our conditional reads like this. If I go to college and something, then I go to college. Or even if you just got rid of the word and. If I go to college, then I go to college. Well, duh. That seems kind of obvious. But as we've learned in symbolic logic, sometimes it's not clear if a statement is true or false. And in this case, it might not be always true, and it might not always false, depending upon the truth values of the simple statements. The simple statements being I go to college and I take math. It just so happens I go to college shows up twice. So is this statement always true? I mean, it sounds like if you say a statement of the form, if I go to college and do some other stuff, then I go to college. It sounds like it ought to be true. But one way to find out is to represent it symbolically and then construct its truth table. So let's figure out how to represent this statement symbolically. Then we'll build its truth table and see what happens. Oops, got ahead of myself there. Let's go ahead and represent it symbolically. Again, in order to represent it symbolically, we have to locate these simple statements, and the simple statements are pretty just easy to pull out there. One of the simple statements is I go to college. So we should probably call that something. Let's call that P. P equals I go to college. And the next simple statement is I take math. So we will call that Q. I take math. And we do have another simple statement, but it's a simple statement that's already been defined. I go to college. That was not supposed to do that. It was supposed to do this. I go to college. So let's see if we can translate this into symbols. This is primarily a conditional, evident by the comma and the word then following it. And so we'll go ahead and set up a conditional arrow. To the left of the conditional is, to the left of the arrow is the antecedent, but the antecedent is a compound statement in its own right, and so it will have to go inside parentheses, and the connective there is an and, so it's a conjunction. The statement to the left, I go to college, is statement P. The statement to the right of and, I take math, is statement Q. The consequent, the statement following the word then, is I go to college, which is P. So symbolically, our statement is parentheses, P and Q pointing to P. Or you could also say, if P and Q, then P. All right, now let's go to the next page where we already have this set up. All right, you'll notice I've already got the first two columns of the truth table set up. And in the homework and on your test, the different truth values of the simple statements will already be provided for you, and they will be provided in the same order every time. I've already got the correct number of columns set up, but let's remember how to figure out those columns. You look at the statement that you're building the truth table for, and using the hierarchy of connectives, determine the order in which to build the columns. We have parentheses, so we go inside of there first, and inside those parentheses is a conjunction, and that conjunction will happen first. That's the only connective inside the parentheses, so we move outside the parentheses, and the only connective out there is the conditional, so that will go second. So our first column in our table will be P and Q, or P conjunction Q, and the second column in our table will bring in the conditional and the entire statement. All right, remember to complete a truth table, you go one column at a time. So we'll do this column first and this column second. And for each column, you ask yourself two questions. The question you want to ask yourself first is, what rule are we going to use? Well, since the first column is a conjunction, the rule for conjunction is it's true when it's all T's. In other words, a conjunction is true when every part of it is also true, otherwise it's false. So let's look on each row and try to find where we have all truths. This row has all truths, so that is the only row, well, excuse me, that's the only row that's all true. Let me slow down for a second. We know what we're doing. We're applying the rule true when all true. Then you ask yourself, okay, which previous columns am I doing it to? Well, on both sides of the conjunction, we have a P and a Q, which allude to the first two columns, as if I had a choice on this first one. So we're looking in the first two columns and we're applying the rule true when all T's. The only row that's all T's is the first row. So that is the only row where this column will be true. Since none of the rest of the first two rows are all T, that's not all T. Oops. I wanted to move that. That's not all true, and that's not all true. None of these rows follow this rule. So none of these rows will be true, which means all of those rows will be false. False, false, false. All right, let's clean this up. All right, moving on to the second row. The second row is built around the conditional. Excuse me. And so we need to first ask ourselves, what is the rule for conditional? The rule for conditional is the broken promise, meaning that it's false only when we have T pointing to F. That is the only time an if then is true. So that's what we're going to do. But what columns are we going to do it to? To the left of the conditional arrow is P conjunction Q, which is this column. And to the right of the conditional arrow is just Q, which is this column. Since we're not using the first column, I'm going to cover it up. I would not recommend scribbling it out, although since we're about to fill out our last column, it wouldn't be the end of the world if it was scribbled out. And now we need to apply the rule. But remember what I warned you about in a previous video. When you're doing a column for a conditional, you read it left to right. So this pointing to that. But the columns that you refer to may not be in that same order. In this case, we need the conjunction pointing to Q, which means we need to look at this as pointing from right to left, the conjunction pointing to Q. Now, you don't have to physically draw these arrows, but when you're doing a conditional, the order matters. It has to point from the antecedent to the consequent. Now that we know what we're doing and which columns we're doing it to, let's just apply this rule. I'm going to look for I'm going to look for T pointing to F, and when I see it, I'm going to put false in the second column, one row at a time. Is this T pointing to F? It is not. Is this T pointing to F? It is not. Is this T pointing to F? It is not. Is this T pointing to F? Again, it is not. None of these rows follow this rule. Excuse me. None of these rows follow this rule right here. That means none of these rows are false. And if none of the rows are false, then that means only one thing, that all of these rows are true. And to be honest, we kind of expected that. Let me pause and clean this up. There we go. And again, to tell you the truth, we were kind of expecting that because it seemed like from the very beginning that this statement was always true. But that's the great thing about symbolic logic, is that you don't have to have guess or rely on a hunch or something. You translate words to symbols. You determine the correct order in which to build your truth table. You build your truth table using the pre-established rules for negation, conjunction, disjunction, conditional, and biconditional. And at the end of the table, you know something about the truth value of your compound statement. But it did so happen that this one was entirely true. Since the statement P and Q pointing to P is true for every possible combination of truth values for its simple statements P and Q, translation, the last column was all trues. This statement is called that was anticlimactic. This statement is called a tautology. So by definition, a tautology is a statement that is always true, regardless of the truth values of the simple statements it contains. Now, there are some statements that are obviously true. That one we did may not have been as obvious, but how about this one? What if I said, my name is Chris. Let's make that font size a little bit larger. Or my name is not Chris. I think we would have to accept that as a tautology, because one of these two has to be true. One of these two statements, my name is Chris or my name is not Chris. Because think about it, either my name is Chris or my name is not Chris. If my name is Chris, then this is true. Disjunction looks like that. My name is Chris would be false, but the rule for disjunction is it's false only when it's all F's. This doesn't follow that rule, which means this is true. But if my name is not Chris, then this is false. Disjunction looks like that. If my name is not Chris, then the second simple statement is true. And again, the rule for disjunction is it's only false when it's all false. This isn't that case. This is true. So whether or not my name is Chris or my name is not Chris, the statement ends up being true all the time. Now, granted, we didn't construct a truth table, but this really only had one simple statement. That simple statement was my name is Chris. If you translated it, it would be P disjunction negation P. And since it only has one simple statement, it would only have two rows. What if P is true? What if P is false? I wouldn't recommend bypassing a truth table. I just happened to do it on this one because it was a pretty simple statement. It was a pretty simple compound statement to analyze the truth value of. All right. Let's see if the following statements of tautology. I go to college and take a math class, and I don't go to college. Well, wait a second. You just said I go to college. And then you said, and I don't go to college. How can you do both? Well, do you think this statement's always true? Or do you think something's up with it? And again, the great thing about symbolic logic is you don't have to rely on a hunch or intuition or a guess or anything. You just attack it head on and see what happens at the end. What was just a flash to you was about 15 minutes to me as I got barraged with emails and text and even one visitor, but that's okay. That just means I don't remember the very last thing I said, so we'll start over on this page. We're going to see if this statement is a tautology. I go to college and take a math class, and I don't go to college. Well, that sounds weird. I go to college, and I don't go to college. Well, do you or don't you? What's wrong with this statement? But then again, on the surface, you know, sometimes it's hard to look at a statement and go, that's clearly a lie, or that's true, or that's false, or sometimes it's true, sometimes it's false, but that's why we have symbolic logic. So first, let's represent this class symbolically using the same simple statements as before. P equals I go to college, Q equals I take a math class, and as insignificant as it seems, there was a missing space there. All right. So first let's figure out where the primary connective is, because I see two ands, but only one of them follows the comma. So there's our primary connective, and to the left of it, we have another compound statement, which means it's going in parentheses. I go to college is P. This and is a conjunction. I take a math class as Q. And on the right side of our primary connective is I don't go to college, which is the negation of P. So we will construct the truth table for this to see if the statement is a tautology, although something rings a little weird about it again, because I'm saying I go to college and I don't go to college. All right, so let's build the truth table for parentheses, P and Q, close parentheses, and negation P. First, let's figure out the correct order. There's a set of parentheses, so we go inside of there and do that first. Then outside the parentheses, we have a conjunction and a negation. And in the hierarchy of connectives, the negation takes precedence. So the negation will occur next, followed by the last conjunction, wrapping up the entire compound statement. All right, so our first column is for the conjunction, or P conjunction Q. And let's not dilly-dally on this one. We do know what the rule is, but for consistency, I'm going to type it down here. The rule is conjunction is true only when all true, only when all T's. And of course, we are looking at P and Q, which are these columns over here. And speaking of columns, please forgive me, I didn't label them. It's not critical that you do. It's just good for reference purposes, especially when you're teaching. But I digress. We are applying this rule to these columns. And we're looking for anywhere where it's all T's, and here it is. That's the only row that's all T's, so that's the only row that follows the rule true when all true, which means the rest are false. Let me clean this up. All right. Our second column is the negation, and that's attached to the P. This one's pretty trivial. To find the negation, we simply change the truth value. So let's make a note of that. Change truth value. And there we go. And let's make note of which column we're doing it to. The negation is on this P. The P is over here. We have another case of a lot of stuff in the middle that's in the way, so I'm going to cover it up just for a moment. We don't need any of that. If you're doing this, you can use your finger or something you're writing with or anything to cover up the columns you're not focusing on. So we're going to change the truth values of everything over here. Since it's true, true, false, false, that means this column will be false, false, true, true. Let's clean this up. That little flash was another sort of long pause, so let me just quickly get us back to speed. We are in the process of building the truth table, and we just finished the second column for the negation of P. So we're on the third column, which is for the last conjunction, and let's focus on what we need to do here. This column was built around the conjunction, and the rule for conjunction is the same as it was over here. In fact, I can just copy and paste this. Not that it would take that long to type it. All right. So we're using the same rules before, but which previous columns are we looking at? We are looking at the column to the left of the conjunction, which is this entire parentheses, which is this column, and the column to the right of the conjunction, which is the negation P, which is this column. So we are doing this rule to these two columns here. Let's cover up the columns we're not looking at, so we're not distracted by them. And now let's play out the rule. The rule says T only when all T's. So let's look at each row and see if we can find one that's all T's. Is this all T's? Nope. Is this all T's? No. Is this? No. Is this? No. None of these rows are following the rule, which means none of these rows are true. Well, if none of the rows are true, that means that all of them are false. Huh. Well, we know one thing for sure. This isn't a tautology, because for a tautology, this would have to be all truths. And in fact, it's about as untautology as you could get. Oh, that's what I just said. This statement is about the furthest thing from a tautology as you can get. Instead of being true all the time, it's false all the time. Well, such a statement is called a self-contradiction. So we're about to define a new term. Oops. A self-contradiction is a statement that is always false regardless of the truth values of the simple statements it contains. So you could literally say that it is the opposite of a tautology. A tautology is a statement that is always true. A self-contradiction is a statement that is always false. Let's do one more, and then we will go through this one rather efficiently. I invite you to pause the video and see if you can determine if the following statement is a tautology, self-contradiction, or neither. Because remember, in general, a statement is true sometimes and false sometimes. So being a tautology or being a self-contradiction is more of an exception. The statement is, if I go to college or take a math class, then I take a math class. Pause the video, see if you can translate this symbolically using the same simple statements as before. P is I go to college, Q is I take a math class, and then construct the truth table for it to see if it is a tautology or a self-contradiction, or possibly neither. Go ahead, pause the video. Why aren't you pausing? Hopefully you paused. All right. So let's start with the symbolic representation. This is primarily a conditional because of the then following the comma. So let's start with that. To the left of the arrow is the antecedent, the statement that follows the word if you will. I go to college or I take a math class. But that antecedent is a compound statement in its own right. It has a connective of or, which means it will go in parentheses, P or disjunction, Q. And then the right side of the conditional, the statement following then, is I take a math class. That was Q. Let me go back to make sure I got my P's and Q's sorted out. P is I go to college, Q is I take a math class. Yes, our symbolic representation is correct. And we have to determine the correct order in which to build the truth table. There's a set of parentheses, and so the contents of it will be addressed first. Inside of there is only a disjunction, so it will happen first. Outside the parentheses is the connective, that will happen second. What is the rule for disjunction? I'm not going to write it. The rule for disjunction is false only when it's all F's. So we write F when it's all F's. Are there any rows in these two columns? Is there any row that's all F's? This one. That's the only row that's false, according to the rule for disjunction, which means the rest of the rules are true. Let's clean this up. Excuse me. Okay. Our second and final column is for the conditional. We already decided that up here. And what is the rule for conditional? Conditional is false when you break your promise. In other words, conditional is false when T points to F. Let's focus on the columns that we need to focus on. To the left of the conditional is this disjunction, so this column. To the right is Q. So we got a couple of things to make note of. Thing number one, We are not concerned with this column, so I'll cover it up for a moment. But thing number 2, and probably more importantly, is our columns are in reverse order. We want the disjunction pointing to Q, so we have to point from right to left. Disjunction pointing to Q. And now let's follow the rule. Are there any T's pointing to F's? Only one, right here. That is the only T pointing to F, which means that is the only row that follows the rule, which means that is the only row that we write false. The other rows are true. Let's clean this up. All right, so now we can answer our question. Remember, the question was, determine if the following statement is a tautology, self-contradiction, or neither. Is it a tautology? No, the last column would have to be all true. Is it a self-contradiction? No, the last column would have to be all false. Since it's not a tautology and not a self-contradiction, it is neither. So the things to know from this video are, a tautology is a statement that is always true, regardless of the value of its simple statements. And a self-contradiction is a statement that is always false, regardless of the values of its simple statements, the truth values of its simple statements.